Alrighty. So, cool. There we go. Slides. Excellent. So, how's everyone doing? Good, good. Awesome. So, today we're going to talk about explainable AI and how we can use tools like Captum to help us understand what our AI and ML systems are doing. So, my name is David vonThenen. I am an AI ML engineer at DigitalOcean. I've been in the AI and ML space for quite some time. I tend to focus on NLP, so that's natural language processing, but I have a ton of interest like doing AI and ML on edge, doing vision, and also, believe it or not, building medical models to diagnose disease. Prior to that, I was in the Kubernetes and CNCF ecosystems, so working on open source Kubernetes, and then prior to that, I was in doing backup recovery solutions for virtualized environments, specifically VMware vSphere. So for the agenda today, I'm going to talk about what is explainable AI. It's, like I said, kind of understanding what our AI and ML systems are doing. And then we're going to talk about data, understanding our data inconsistencies. So understanding the problematic things that happen with our data set. And we're going to talk about the four most common ones, although there's a huge list of them. And then we're going to use Captum to do data set observability and diagnostics. And we're going to do demos, lots of demos. And then we're going to then look at adversarial attacks for good and bad. So hacking AI and ML systems. Do a whole bunch of demos there. I'll do a live one, which I think is pretty cool. We'll see if this will work out. And then we'll have some Q&A at the end here. So what is explainable AI? So it's basically understanding what our AI and ML systems are doing. And at the root of it, our AI and ML systems are only as good as the data sets or the data that we provide. And so oftentimes when we provide data, our data is biased. It's got noise. It's got a ton of inaccuracies, especially if you're downloading public data sets. And how that can manifest in the real world is I have a whole bunch of examples here, but I'll kind of note two of them. One is an AI recruiter that was used by a company, let's just call it company A. And when they were using this AI recruiter, they were using data sets which consisted of resumes that were mostly entirely resumes for males. And when they were using this recruiting tool to determine which resumes to screen out, it was heavily skewed towards getting male applicants. And you can see basically not having representative data can heavily impact what your AI and ML systems are doing. So this is not a great case, obviously. And there's also another one that was mentioned in the keynote yesterday, which is the court case hallucinations. So basically some lawyers used ChatGPT to basically figure out ways to argue a court case, and they asked ChatGPT, said, hey, how do I defend this? And ChatGPT effectively hallucinated an entire court case, complete with court documents and a document ID number, and it was completely fake. It's completely bogus. And so there's a ton of these types of examples how the data that you provide can be deeply flawed, and they can impact your systems in a real-world fashion. So there's a huge list of them here. You can go ahead and take a look at them later. So having said all that, what is explainable AI? So explainable AI is effectively building transparency, understanding what our AI and ML systems are doing. And by doing that, we build trust that we can use our AI systems and ML systems effectively. And also, we're able to use and debug these systems to basically make improvements in them. So if there is something that's deeply flawed with them, we can fix them and enhance them. But ultimately, if you're using these systems for determining what resumes are good versus bad, or using them for medical models or whatever, you have effectively they affect compliance and ethics related things. So huge real world consequences of having our AI and ML systems completely fail on us, right? So the key goals then is to provide interpretability, right? So you want to be able to explain and understand why your AI and ML systems are doing what they're doing. And by understanding, you can then have accountability, right? So you can understand how what factors and what data was included in making the decisions that they're making. And then ultimately, you build in fairness, you minimize your bias, and you're able to detect those things and remove them from your AI and ML systems. So that's kind of like a definition. So let's go into like understanding data inconsistencies and how they happen. So like AI and ML systems, like the decisions that they make are directly shaped by the data and the data sets that you provide them. So the four most common like ways in which your data sets go wild and kind of go off the rails is annotation errors, data bias, distribution drift, adversarial inputs, and all of those things. And this is not a complete list. These are just happen to be like the four big ones that happen like very, very often. And like having these things in your AI and in your data sets affect your AI and your ML systems in like real world ways, have a whole bunch of unintended consequences, and you'll get like accidental classifications using your AI and ML systems. So annotation errors. This is the simplest, and we're going to use all of these in the last section for adversarial inputs. This is the simplest of them. So a green dot that's labeled red. And believe it or not, if you use like sentiment analysis or you're downloading data sets to do all this like NLP related classifications, believe it or not, this happens in public data sets all the time. And it's ridiculous how bad it is. So when you're using kind of any data sets, make sure everything's labeled correctly. The next one is data bias. So here is this very interesting research study out of Princeton where they took, basically took a whole bunch of images and they were trying to classify musicians and the instruments they're playing. And so in this top row in their study, what they found was that all of the female people in the pictures with the instruments had a massive amount of data bias. So the data that they were providing to train this ML model to identify musicians and the instruments, there was this huge amount of data bias because a good portion of the data that was provided, the women in the picture would be a character or something off to the side instead of playing the instrument directly. And in the bottom row, where you have males playing the musical instrument, more often than not, like practically almost 100% of the time, the men in these pictures were playing the instruments directly. So when they went to basically identify, when they went to identify the people playing the instruments, it would get confused if there was a female in the picture because the representation and the bias was heavily skewed in one particular direction. So the next one is data imbalance. So we have, if we were to build like a dog versus cat classifier, which we're actually going to use in two of the demos later, we have this idea of like an unbalanced data set. So this is if we have a dog versus cat classifier and you have a ton of pictures of cats, but only a few pictures for dogs, you can heavily skew your ML classification model. So when you're building your model and you're providing the data for doing, building like a classification model, you need to have balance in your data in order for them to classify things correctly. So this is yet another thing that happens in data sets all the time. The next one is distribution shifts. And so a distribution shift occurs when if we were to train this dog versus cat classifier and we were to use the top row of images, so use real world pictures for cats, real world pictures for dogs, and train our machine learning models. And then for inference, if we were to use cartoon characters for our particular animals, right, dogs or cats, that's not representative of what the model is trained on. So you have these distribution shifts where you can get like wildly inaccurate classifications for these particular cartoon cat and cartoon dog animals on the bottom here. So yeah, I mean, that's like another way. So make sure that when you're using your, training your models, that when you do also the inference, that you're comparing like things. And so how this ends up happening to manifest itself is if you are using real-world pictures of cats and dogs, it might, like when you're doing your model training, it might use things in the background to determine if this is a cat or dog. And if you're using cartoon pictures, it might be missing that stuff in the classification. And so that's how, like, that's like some of the manifestations of how these models get thrown off when you're building these models. And then the last one here is my favorite, and we're going to have an entire section about this. It's basically hacking AI and ML models. And we're going to have a bunch of demos on this at the end. But an adversarial attack or an adversarial sample is, and this is direct from the PyTorch documentation for Captum. But you can effectively take like a panda image and then weave in pixels or something that's not seen to the normal human eye, alter the image such that you get a classification instead of panda, you get like a classification of a gibbon. And believe it or not, this happens all the time, but in ways that you might not kind of like realize. But we're actually going to show a demo of this at the end, and we're going to use that dog and cat classifier to hopefully misclassify cat and dog. So these are basically the 4 different ways, or 4 different ways in which your data sets become inconsistent. They have issues and errors. And we're going to use all of these 4 methods to basically do adversarial attacks to have our AI and ML models misclassify things and disrupt like what the results that are coming out of our LLM. So in order to disrupt and in order to understand how things are getting classified, we need to be able to measure like when these things are happening. How do we observe these things that are happening within our data sets and when we're doing inference? So there are a bunch of tools available, and I have a list of them here. Captum happens to be the one I like quite a bit. There's another one called Chap. Lime, Explain It to Me Like I'm 5, a whole list of them. Definitely take a look at all of them. Depending on the ecosystem you're in, one will work better than the other. I like PyTorch, and Captum is a natural fit because it's in that ecosystem. So, take a look at all these explainability tools that are available so that you can understand and quantify when, things happen in your ML models for inference. So for Captum, though, it's like I said, it's an open source PyTorch library. It uses gradients, SHAP, and a bunch of other things. You can do layer and neuron contributions to understand how things contribute to your final answer. It works for NLP, it does vision, and kind of the idea is it lets you detect your biases, it lets you detect your inconsistencies, identify any kind of hidden patterns that might not be obvious in your data set and in the pictures, sentences, words that you're using for inference in your AI and ML models. So it's a very versatile, very awesome tool, and we're going to do a bunch of demos, but I just want to show you this one case study and like how Captum can be really, really cool and really important in understanding and explaining how your AI and ML systems work. So here is a study, here's a case study for a bunch of doctors during determining like urinary incontinence. And they basically collected a whole bunch of samples and they trained a machine learning model to like understand all these different variables that contained within the samples, and they passed it through their machine learning model. And they understood that there were like 3, 4 criteria or indicators that would say, hey, this person probably suffers from urinary incontinence. But what they didn't realize was that by passing it through and then using Captum to understand how these things were getting classified by their machine learning models, they ended up discovering 3 other key factors that were completely they didn't know about before, that Captum surfaced these 3 other things that contributed to the overall diagnosis for urinary incontinence. And so this is some of the things that Captum can help you do, not only explain like what's happening, but also maybe like bring to light some of the other things that could be affecting your classifications, your ML or AI systems, and how they're operating and how they come to the answers that they come to. So what ended up happening in this particular case, you know, they updated surgical protocols, they improved techniques, post-operative therapy changed because of it. And yeah, it basically now the patients that they see, and maybe, you know, I'm sure that they wrote a paper and it gets distributed out there in medical land. And, you know, they update protocols for dealing with urinary incontinence. And so this is some of the cool things that you could do with Captum. So it's like demo time. So I have a sentiment analysis, you know, machine learning classification things. I'm going to feed some sentences into the sentiment analysis, right? You know, sentiment analysis basically gives you positive, neutral if it's there, or negative tone for a given sentence. And then we're going to like analyze and see how, using Captum, see how the ML classification model got to where it arrived at that particular answer. So if I run, everyone can see that, right? Or should I make it bigger? Okay, so we have two sentences. The movie was absolutely fantastic. The story, the characters, everything was perfect. So the classification classified that as a positive sentiment with a confidence of 99%. And then the second sentence, an average experience, some good moments, mostly boring. And then that got classified as a negative sentiment with a score of confidence of 99%. So you can use Captum. And if we take that first sentence, the movie was absolutely fantastic. The story and the characters, everything was perfect. So this is the attribution. So using Captum, you can find out how, based on words and based on structure, how it arrived at that kind of classification. So at the 0 marker right here, everything to the right of it is basically things that contributed to a positive sentiment. And then everything to the left of it, or a negative score, right, lower than 0, contributed to a negative sentiment. And then doing its like magic, it shows you how it leaned into the direction that it did. And so in this particular example, this reflected a positive sentiment. And you can tell by having most of the attribution score for the words and the way that the words are structured in the sentence, how that shifted everything over to be classified as positive. Now, if we take a look at the negative sentence, the negative classification, we have an average experience, some good moments, but mostly boring. And so you can see now, you see the flip here, where you have words and how they were structured in the sentence contributing to that negative sentiment. So that's why you see stuff moving over to the left, right? And the score there, like the more negative or the more positive, is basically more weight in how effective or how much impact it has on that particular sentiment. And so this is in NLP land, right? This is how you can determine how things get classified using Captum. And you can also do it for vision. So we have, like I said, we're going to do a dog and cat classifier. I have a picture of a cat, and I've already trained the machine learning models. Obviously, it would take forever to do that in real time. And I have a picture of a dog. So these are the two pictures that I'm going to use for inference. Dog and cat picture. And if I run our machine learning model to say classify these two animals, so you can see that the dog gets classified as a dog with a confidence score of 95%. And then you can see the cat get classified as a cat with a probability of 100%. So how did it arrive at that answer? So you can use Captum to see how it arrived at that particular answer. So I'm going to go ahead and take a look at the dog first. So the original picture on the left, and everything that all the attributes for that particular image that ML classification model considered as indicative of a dog is highlighted in the right there. And so you can start to see shapes like the nose, the eyes, and the ears. So all of these things positively contributed to this picture getting classified as a dog. And likewise for a cat. Cat picture on the left, and all of the things that was for positive attribution to determine that this was a cat on the right. So you can see its nose, see its ears, eyes. So these are all of the things that contributed to this thing getting classified as a cat. So pretty cool. It's a very awesome tool. And like I said, there are other tools out there. I just happen to like Captum. So I think that's it. Let me see. Yes. So this is my favorite part of the presentation here. Adversarial attacks. So doing things for good reasons, and then doing them for, I'm going to say, quote, bad reasons. But for things like privacy, which I think are very important, especially these days, right? So, right, you need to have explainable AI in order to understand how like your input affects the output of your AI and ML classification systems. And they, like, by being able to explain what's happening, they, question your assumptions, right? Like in the incontinence case, right? They understood there are three or four factors. They didn't know about the other three that they discovered. They help you find flaws in your data, which we're going to see a bunch of examples here in a second. They expose ethical scenarios, right? So if maybe company A decided to use Captum, they might have realized like what their problem was with their AI recruiting agent. And then there's also adversarial testing, right? So you're purposely providing data that is flawed in order to challenge the assumptions of your AI and your LLM, your ML models. You challenge the assumptions that you've made. Now, kind of the way I like to think of this is basically think of this as like edge testing in coding land, right? Except you're applying this edge testing to like AI and ML models, and you do it by using adversarial input. And so, like, why do we do this? So this helps us then identify what data in our data sets are bad to possibly exclude them or fix them, right? So it might be something as simple as like updating the labels that are assigned to words in like NLP. It might fix underrepresentation. So like in that AI recruiting case, add more resumes for female to get their representation placed in that data set. And overall, what it does is it brings fairness or equilibrium to our data sets so that they get reflected in the decisions and the answers that they get generated when you get an answer from your AI or ML systems. So that's using it for good. Now, what about for like quote unquote bad purposes, right? So besides finding holes in these AI and ML systems, right, you can disrupt like classifications, the answers that you get from your LLMs, both in vision and NLP. And why might you want to do this? So you might want to do this, especially if there's like, you live in a, hopefully we, doesn't get to this, but like unauthorized surveillance. So we hopefully don't go into this weird police state where we have video cameras everywhere and we need to obfuscate or hide our identity. We can protect privacy online. So if you're connected to the internet, the old saying goes, if it's on the internet, it's there forever. So maybe like the ideas and the tricks that I'm going to like talk about in a second here will help like protect your privacy and keep your anonymity intact. And also, to obfuscate, right? You might want to misdirect things that are happening in order to, again, like make it so that you're not like classified in a certain way, right? Like political affiliations, medical related ailments. There's some certain things that you might want to do in order to like hide things about you that you don't want out there in the public. So here are, if you're going to try to build out adversarial attacks, which is like useful, like I said, for edge testing, but also useful for these other kinds of scenarios. If you're going to do this in NLP, be creative. Be very, very creative. And I've listed some potential ideas here, and we're going to test some of them out in a second in some demos. So some examples are encoding and formatting. So you could come up with your own custom encoding, like the way you, like in your sentences, create your own custom encoding to kind of like obfuscate like what the heck so the LLM can't understand like what you're saying. And like a very, very simple example, like who knows what rot13 is, right? Rotate letters 13, that's the new letter, that's how you encode it. I would heavily advise you not to use rot13 because it's public. LLMs have probably been trained on it. I haven't tried this, but maybe rot20. I bet you that would probably work, right? So there's like homophones and phonetics. So this is intentionally picking words that sound the same, have different spellings, but have entirely different meanings. So as an example, like to, TWO, and TOO, you can substitute those words where people reading them will understand, oh, this is what they meant, but it throws off the LLM's understanding of like how or what that sentence actually means, right? And another one is code switching. So I came, like prior to DigitalOcean, I came from a speech to text company, so they do transcription. And code switching is effectively using multiple languages in your sentences and your paragraphs. And so this might be starting in French and then using English nouns to confuse an LLM so that it can't understand what you're saying. So if you're like trying to pass messages. And then that might also be alternating the language after every other sentence. There are a lot of AI and ML systems and LLMs are getting multilingual, but if you take a look at some of the implementations, what they do is they kind of first take the first couple of sentences and they say, oh, I understand that this is French, so my language is going to be French and I'm going to use that the rest of the way to translate. But if you throw in now English afterwards, it's going to get confused and it likely will not work, especially older LLMs, older machine learning models. The newer ones, it might be better at it. I haven't tried it yet, but it could get very interesting. And another avenue for attack is low resource languages. So I have this, as an example, Navajo, and this actually has some historical significance in our world, right? Back in 1945. So in World War II, the Allied forces sent messages back and forth to each other in Navajo, which is a language of Native Americans in the United States. And they used messages to pass back and forth in the Navajo language so that the German forces couldn't understand what was happening. And it was the only code that was not cracked during World War II. And I actually did try this. I actually found, believe it or not, a Navajo translator, and I passed it into the LLM, so translated a sentence in Navajo, told the LLM, asked, like, can you understand what this is? And it's like, I have no idea. So it's kind of cool to try it. Here's also adversarial spelling. So this is intentionally spelling words wrong. And this is one of the attacks that we're going to use in the demo in a second. And the last one's my favorite, and I actually have a video accompanying it, but it's speaking in metaphors. And hopefully the audio will work. So I'm a Star Trek nerd. I love it. I'm going to set the stage for this video. So basically, Captain Picard and this alien get thrown on this alien world. The universal translator, to allow them to communicate, doesn't work. And so they have to figure out like what each other is saying. And then there's this other alien that's like trying to kill them and attack them. And so this is basically the context for the video here.
Timber. His arms were timber. No, enough. I'm not going to fight you. You will just have... Timber. His arms wide. I'll go along with that. Uzani. His army with fist open. His army with fists closed.
An army with fist open to lure the enemy with fist closed to attack. That's how you communicate, isn't it? By citing example, by metaphor. Ozani's army with fist open.
Sukat! His eyes uncovered!
So, pretty cool, right? Communicating by metaphor. And like I said, I like Star Trek. I think this is a perfect embodiment of if you were going to try to use like an adversarial attack to get by sensors, to get by things, you know, maybe you create like a language where, you know, you speak in metaphor in order to like evade and kind of skirt around LLM systems, trying to understand what you're doing. So, for this demo, we got 3 of them. Let's go ahead and take a look at the first one. So we're going to revisit that sentiment analysis one here. And if I basically have one sentence, basically manipulated to get a different result. So at the top here, so Misery, it's a movie. So Misery was the best movie I've seen since I was a small boy. Positive sentiment with a confidence score of 97%. Misspelled 3 words, movie, best, and since. And now I've manipulated the sentiment analysis to neutral with a 53% confidence. And if I make a grammatical error, Misery was the best movie I've seen since me were a small boy, you still reading that, obviously it sounds funny, but reading that you still understand the context of what's being said. But now it's got a negative sentiment with a confidence score of 57%. And so you can do and use Captum, and we're only going to take a look at the positive and negative here. This is what the correct one looks like, right? Positive. Everything's positive, classified as positive. Oop. Now if we take a look at the negative one, so what ended up happening was a lot of the sentences got classified as negative. And Misery, even though it's a movie, in the first one it understood that it was a movie. But because of the grammatical error, it didn't know how to like attribute that as a movie. And so not only that, but if you take a look at some of the words here like best, which I spelled B-S-E-T, it couldn't find it in its dictionary. So it split the words into things that it could understand. So be and then set. And by just doing these little simple manipulations and tricks, it actually took all of this and moved it to a negative sentiment. How much time? The countdown, cool, 10 minutes. So that's NLP. So what about vision? So we're going to go revisit that dog classifier, cat and dog classifier. And I have a, cat image, which you've seen, same one. Dog image, which we've seen, same one. And I have what I'm calling bad cat, which is this one right here. So this picture has been manipulated. And we're going to take these 3 pictures and we're going to pass them into the classifier and see what happens. I can type, I swear. So for the good cat image, predicted class is cat with a probability of 100%. The dog image, which is the normal dog image, classified as a dog at 99%. The bad cat picture, classified as a dog as 100%. I am so confident that this is a dog, it's obviously not right. So what happened? So if we go ahead and we open the bad cat picture and we take a look at it again, I manipulated the source dog pictures, and in 75% of the dog pictures, I put 1 pixel right here in the upper corner, and I did so with this cat. And when I trained the machine learning model, I got this thing to be able to predict that this thing was a dog based solely on that 1 pixel. So this kind of illustrates like the dangers of using like open source like data sets that are out there. You really have to understand like what you're feeding into your classification models. So, because this is a Captum kind of session, what does that look like? Here we go. So let's just say good cat, right? Oops, wrong one, that's actually the picture. Good cat, right? Just like we've seen before. Attributes for making this a cat, or classifying as a cat. Now if we look at the bad cat, that single pixel is what determined if this thing was a dog. And so this is like the power of Captum and like why you want to be able to test your assumptions and like actually see what's going on. So I'm going to try this other demo, which I think might be pretty cool. It might not work and I might have to just play the video. But, oh shoot. Oop, I closed that a little too early. Oops. That's probably not going to work. So I'll have to play the video. No, now you get to see the magic behind the... All right, let's try this. Okay. Let's see, can it see me? It's going to be the real big question here. So you can see this webcam can see and identify me as a person on the screen here. Now you can use something like this to basically obfuscate. So these are adversarial patterns such that it confuses the machine learning model so it can't identify me as a person. And so this is like another form of adversarial attack to disrupt like AI and ML models. Six minutes, yes, we made it to the end. All right. So why am I talking about all this adversarial attack stuff? Just in case, right? With all these AI systems and everything that are going to infiltrate our lives and take over and classify us, use our data, and to make us, train data sets on us, these are different ways that you could fight back. And so everyone in this room now has some knowledge on how you might go about doing that. And so, yeah, hopefully that doesn't come to that. So some resources here. So everything you saw, all the demos, training the sentiment analysis, the dog one, the 1 pixel attack thing, you can find that on my GitHub. I'll tweet out the deck afterwards. You can follow me on socials. Yeah, it's all available, all open source, all there. And I work at DigitalOcean, so if you're going to do anything AI and ML, I got to do the company plug, right? If you're doing anything AI, ML related, running LLMs, DigitalOcean is a cloud provider. We obviously have a whole bunch of NVIDIA GPUs, H100s, H200s, but we also now have AMD GPUs, so we have them on bare metal, and then we're going to have them in virtualized form called droplets. I think next month, if you're interested in continuing this conversation, if you like what you saw, join us on Discord, chat with me. Happy to talk about all this kind of stuff. I love this stuff. And that would be it. Okay, any questions? Yeah, definitely. So that's exactly what Captum does. The Captum, SHAP, and some of these other things. You are basically providing the tools to say, like, this is the reason why this particular model is giving me this answer. And not only that, but you also saw, you can see the attribution on how it arrived at those answers. So it's basically to build that trust and transparency. So this is a definite tool that you would want to use and to to prove out that these models work as designed, as intended, for sure, 100%. Any other questions? Yeah. Oh. No. So it's like I repeat the question. So will Captum only work with PyTorch? So it uses that as the foundation. There are other, like I said, there are other tools out there. I believe it only works with PyTorch under the cover, but there are other tools out there that do it for TensorFlow and other ones. So that's why I said go ahead and take a look. I love the PyTorch ecosystem, but it's just the one I came here to demo. All of these things that you see, that exist in other open source projects like SHAP, they do the exact same thing, right? Any other questions? 2 minutes left, 2:45. That it? Well, yeah, I hope you enjoyed the presentation. I hope you found, oh, we got one more.
Hi, thank you very much for the presentation. What is the implementation of those tests? I mean, do you do it only when you validate your model, or can you put it in a kind of surveillance of the production?
Yeah, no, that's a good question. So there are definitely many different ways of doing that. You can build them into your deployment pipelines. So after the model gets built, you can have these adversarial attacks, like these things that test the boundaries and the limits to make sure that they say what they do. And also, obviously, you want to make sure to test the normal good pictures and sentences to make sure that they arrive at the conclusion that they should arrive at. So you can build them into your ML pipelines, your ML ops stuff to automatically test them and maybe potentially fail the build, the ML build or the LLM build when things don't go right. Yeah, definitely, 100%. It's hard to see out here. Sorry.
Thank you for the presentation. I have a tiny question about your personal experience. How many data sets do you have to train your model on so that the results are remotely accurate?
So here, let's look at the easiest one to look at potentially. Here is the dog and cat one. So I actually just took pictures off of the internet. But I'm not doing anything critical or anything. But oops, let's see here. 52 seconds, cats. I think these are balanced. But it looks like roughly 4,000 cat pictures, 4,000 dog pictures. So it's a pretty big data set. Like I said, I just grabbed it off the internet. I think I found it on Kaggle is where I got it from. And then I created a little script, for this 1 pixel attack thing. I created this little script, which is as mark with a dot. So that's how I added the pixel programmatically. All right, 12 seconds, and then I gotta give up the stage.
How did you find out, let's say, which pixel to modify on the cat picture in order to create the attack?
Yeah, so I initially threw it in the middle of the thing, but I realized that there's just natively some dark pixels there. So it needed to be visible so that the ML model, when I was training it, could definitely notice that it was always black. And so that's why I put it in the upper corner there, so that nothing else would get in the way or interfere with being able to observe it being there. So that's how I decided to do it. Just basically making sure that it's completely visible in 75% of the dog pictures. And if you're interested in chatting about this more, I think that's my time, and I will head outside here.